Hello everyone, welcome to this training session on non-parametric statistics. Till now, whatever the sessions which we have looked at, whatever the various statistical tests which we have looked at, whether it is to do with the mean or comparing of the proportions or even with the variances, whatever are the comparisons which we were doing, they were all, these are the various parameters of any data. But without finding the parameters, if I have to do some kind of conclusions or some kind of predictions, we use the word of non-parametric statistics. Some of the most common kind of tests which we do in case of non-parametric is one associated with the ranks and two associated with the medians. The reason why these two things come under the non-parametric statistics is there is no necessity of the data following any particular distribution like a normal distribution. Even if my data is not a normal distribution, I can very well apply the test from this non-parametric statistics. So from that standpoint, understanding some of the tests associated with the non-parametric statistics is also very well important, because if I find my data not to be normal in nature, or in some cases categorical in the form of ranks, I don't have a direct test which can actually help me in terms of making conclusions about the data. So we will look at a few of these non-parametric statistics and try to see how we can really benefit using this non-parametric statistics. Alright, with that let's move forward. Some of the tests which we will look up as a part of this introductory session on non-parametric statistics is one is the signs test. Because here we are, as I said, we are not too much bothered about the mean, variance and all. So we look at comparisons using the sign, increase or a decrease. That sign test we use for a matched pairs and we call that as Wilcoxon sign ranks test. Or if I do it for two independent samples, if I test for the equality of the medians, I use Wilcoxon ranked sum text. Then just like an ANOVA, if I want to test the equality of the medians of multiple populations, not just two, then I can the equivalent of ANOVA is what we call as a Kruskal-Wallis test. Just an equivalent to correlation, if I want to do for non-parametric, I call it as a rank correlation. And if I want to test whether the data is random or some kind of bias present in the data, I can even go for a runs test. So these are some of the common tests which we will look at as a part of this chapter. Right, so we'll go one by one. So just to differentiate between what is a parametric test and the non-parametric. Any parametric test which we have used, we will talk about the mean or proportions or even the variances. Any of these things we are looking at, we will typically initiate the process of parametric. Because there most of the tests which we are doing, they will involve the nature or shape of the populations. There are a lot of places where we make an assumption that the data will follow a normal distribution. But what if the data doesn't follow a normal distribution? So these non-parametric tests, they don't require the samples to come from a particular distributed population. So they don't expect that the data is normally distributed. So from a practical standpoint, even if my data is not normally distributed, I can still go with the non-parametric test. So basically the advantage comes with wide variety of situations because the requirements are not as rigid as your parametric data, because you don't expect the data to be normal in nature, which may even you don't expect the size of the data should be more than 30. So what is happening is, for a large number of applications or for a large number of business scenarios, you can very well apply this normal non-parametric test, and they don't even expect that your population should be normally distributed. And from that standpoint, even to a categorical data like gender or survey of the respondents, for these kind of scenarios also, your non-parametric test can become very much useful. Whereas when you talk about a parametric test, they are applicable only to a quantitative data but not to a qualitative data. But some of the things which act on the disadvantage side is they are not as efficient as parametric tests. It's like this. If a particular parametric test gives accuracy in X number of situations, probably the same thing done with a non-parametric test may give a 95% or a 90% kind of an accuracy, which means we need more sample size to actually establish a conclusion using a non-parametric test. So that happens to be one of the major disadvantage. But yes, if my data is not normally distributed, or I don't even know what kind of distribution my data is coming from, then obviously the non-parametric test is a much better solution. So whatever we are going to look at in this chapter, these are some of the key things. Matched pairs of sample data, it's more like pair matching, which we have done even in case of quantitative data. A parametric test also we have used a t-test or a z-test depending on whether the population standard deviation is known or not known. In our case, we use these two tests, sign tests or Wilcoxon signed ranks test. We look at the difference between these two tests, but whenever we are talking about matched pairs of sample data, if it's like a paired sample t-test or paired sample test, which we have looked at in the case of parametric, and two independent samples tests. Again, this also we had in case of parametric, testing the uniformity of the means of two independent samples. So we again there also we have used a t-test or a z-test only. Here we will be using, in case of non-parametric, we call that as Wilcoxon rank sum test. And if there are more than two populations, and I want to find out the uniformity of the equality of the means across multiple populations, we were using an ANOVA test. Whereas the non-parametric equivalent of that will be your Kruskal-Wallis test. Similarly, for a correlation, in case of parametric, we call it as linear correlation. When it comes to non-parametric, we talk about rank correlation. And if I want to find out whether any particular data is random in nature or not, there is no test in the parametric space to test whether the data which I am having is random in nature or not. Whereas a runs test is one very good test which can help us in deciding whether a particular data is random or is it more biased in some form. So we'll look at in detail now all these 6 tests which we will be covering as a part of this chapter. We'll start off with the sign test. So before we get into an understanding of the sign test, we need to discuss something about the ranks. How do we assign ranks to the individual items? It's basically simple. Arrange the data in the ascending order or in the descending order, and the lowest one give a rank of 1 and keep on increasing the ranks. Now, the only problem occurs if there is a tie in the ranks. For example, if my data is 20, 23, 23, 23, 27, if this is my data. Now, obviously, this should be ranked 1. Then there is a tie for these 3. So, logically speaking, between 2, 3 and 4, these 3 are getting tied up. And this one is obviously a 5. Now, what the ranking mechanism for our statistical process says is, take the mean of all the positions for which the ranks are tied up. 2, 3, 4. Find the mean of that, which is 3. Assign the same rank 3 to all these 3 numbers. So you will have only 1 for the first one. The second, third and fourth, all 3 of them will have a rank 3. And the next one will have a rank 5. This is the mechanism that would be followed for assigning the ranks. Right? Now, why are we using this sign test? The main objective of using a sign test is with a matched pair of data. So I am having 2 sets of data. For this value, this is the corresponding matching value. I want to test about the median of a population, or I want to test about a nominal data with just 2 categories. So some kind of claims about a pairs of data is what we are doing as a part of the sign test. And I want to find out this particular thing, the number of times the less frequency sign. So what for each item, what I'll do is I'll either assign a plus sign or a minus sign. Let's say I'm talking of 2 categories, male and female. For a male, probably I may put a plus sign. For a female, I may put a minus sign, or vice versa. Or I want to talk about the median. For values which are lesser than the median, I'll put a minus sign. For values which are greater than the median, I'll put a plus sign. So what is happening here? Out of the whole set of data, I am categorizing the entire set of data into 2 signs. I am not bothered about the values, because median is the one that should segregate the data into 2 halves. What I am simply looking at is I am splitting the data into 2 halves, into 2 parts. One is the plus sign, the other is the minus sign. And at the same time, I am trying to find out how many times the less frequent sign has actually occurred. Did it occur? So let's say plus has occurred 10 times, whereas minus has occurred 20 times. So the number of times the less frequent sign in this case is a plus. It has occurred only 10 times out of the total 30. So I would be more bothered about n equal to 30, and I am more talking about the number of times the least frequent sign has occurred. So based on that, I will try to find out what is my test statistic. Right? Now in this case, what would be my test statistic? Because my sample size is 30, I would choose this as my test statistic, which will follow a Z or a standard normal distribution. But if my total sample size is less than 25, I will simply consider X itself as my test statistic. What is X? The number of times the less frequent sign occurs. So now going ahead with it, now taking the same example, I am saying 10.5 minus n by 2, n is 30. So 30 by 2 makes it 15, divided by square root of 30. Square root of 30 works out very close to 5.5 divided by 2. Now what is that we are saying? Minus 4.5 divided by almost 2.75, which will work out to probably minus 1.7 or something. Now, what we are saying, this will follow a Z distribution. Right? We just need to know what is the formula for test statistic. We are not interested in deriving all these things. These have already been derived. So basically from a business standpoint, I need to understand if I have to test a claim about the matched pairs of data, or I want to test a claim about a nominal data which has only two categories, male, female. Is there a uniformity across the males and females? Are equal number of values there below the median and above the median? If these are the kind of claims I want to look at, then I will use the sign test. And as long as I can give two different categories, plus and minus to a data, I can very well depend on the sign test. So out of that, whichever is the sign, plus or a minus, whichever is the sign that occurs the least number of times, I'll consider to be the X, and the total sample, which include both positive as well as negative sign. A neutral sign is not considered. So the total number of positive and negative signs will be added up, and that would be N. And based on that, depending on if my data size, if my total plus and minus signs together is less than 25, I'll directly use the number of times the less frequent sign has occurred itself as my test statistic. Otherwise, I'll use that it follows a Z distribution, standard normal distribution. I substitute the values into it, and let's say I got minus 1.7. Now I can find out the critical value for the Z distribution. As we all know, the critical values for Z distribution with a 95% level of confidence or 5% level of significance is minus 1.96 to plus 1.96. Now I will see whether this minus 1.7 is lying in the critical region, which means below minus 1.96 or above 1.96. If it lies anywhere in this range, I call it as a critical region, and I reject the null hypothesis. Rejecting the null hypothesis is simply saying that there is no difference, that there is a definite difference between the two pairs of values. Otherwise, I can very well fail to reject the null hypothesis and say there is not much of a difference between the two pairs of values. So the median is more or less the middle value, or the two datas, whatever we are talking of, they are more or less the same. The categorical data, whatever are the actual values, statistically the frequencies of both of them remain to be the same. These kind of tests can very well be done using our sign test. So if at all my N is greater than 25, I can be looking at the normal distribution tables. So what are we doing in this? Any raw data that is given, it has to be converted into a plus and a minus sign. So each value I subtract, and I put only the plus and the minus. Let's say here I want to find out the difference between these two matching pairs. Okay, so all I'll do is I'll put a plus here, I'll put a plus here, I'll put a minus, I'll put a minus, I'll put 0 because there is no plus or a minus. Here I'll put a minus, this is a minus, this is a minus, this is a minus, and this is a minus. So overall, what is that? I have 2 pluses and 7 minuses. As simple as this. And so my X, which is the lowest, will be 2, and my N, which is the sum of only positive and negative signs. 0 signs will not be considered, remember that. So my N equal to 9. So because my sample size is less than 25, my test statistic will be this 2 itself. And this does not follow a Z distribution. Only when my sample size is greater than 25, then only it follows a Z distribution and I have to compare it with a Z statistic. Because this is less than 9, I will not go with a Z distribution. We'll have a separate table for sign tests. There is a separate table for sign tests which contains the critical values which are based on the sample size and the significance level. Based on this, I need to look out for the critical value, and in case my test statistic lies within the critical value, I'll go with the null hypothesis. Otherwise, I'll go with the alternate hypothesis. The final conclusion process will remain the same, but the only thing is that does not follow a standard normal distribution, so I have to depend on the exclusive tables for the sign test itself to make the conclusion. Especially if my data size is greater than 25, I can very well use that formula for the normal distribution, and based on that find out the critical values, and based on that get into the decision taking process. So if I want to compare whether there is a uniformity across the two sets of data values, paired data values, I can go with a sign test like this. Then let's look at the next test, which is the signed ranks test. So here also the first step remains the same. I convert the data into ranks, but here I want to test the difference. Each pair has a differences. Let's say pair 1 minus pair 2, whatever are the differences that are there. This is saying if I take the median of these differences, it is equal to 0, which means some of them have lesser. In some cases, they are lesser compared. The left is lesser compared to the right. In some cases, the right is lesser compared to the left. So that's the place where you will have a median value equal to 0. So that is what is the intention. Whenever I am taking the differences between the matched pairs, and if I check that the median of those differences is 0, I am using the Wilcoxon signed ranks test. So simply put, the data more or less will have, two data will more or less have the same median. So if I want to compare the medians of two different data sets, or I want to compare the median of a data set against a claimed value, just like the way we have tested the mean against a claimed value, if I want to test the median against the claimed value, I have to rely on Wilcoxon signed ranks test itself. So some of the important things that we have to understand in this, we don't need that the data needs to follow a normal distribution, but it should be at least approximately symmetric. Right, now we are talking about T. T is nothing but I will find out the smallest of the sum of the positive ranks and the absolute values of some of the negative ranks. Let's take one example. It becomes very easier for us. Let's look at the same data. What I'll do in this case is, first I'll take the ranks, convert the entire data into a rank form. So I'll I'll find out the differences before I assign the rank. Alright, 1, 1, minus 4, minus 3, 0, minus 1, minus 5, minus 8, minus 3 and minus 1. These are the differences. Now go ahead with giving a rank based on the differences, but don't consider the sign of the differences. So don't consider zeros also. So there are 4 ones. If I am going with absolute, 1, 1, minus 1, minus 1. There are 4. So what I do is, because 4 are tied for the first part, 1, 2, 3, 4 slots, the mean of those 1, 2, 3, 4, 2.5. I give a rank of 2.5 to each of them. Right? I give a rank of 2.5 to each of these 4. 4 slots are over, then 5. These 2 are competing for 5 and 6 slots. So the mean of 5 and 6, 5.5. So these 2 will be given 5.5. 5 and 6 are over, so this is given as 7, and this is given 8, and this is given a 9th spot. These are the ranks. Now we also talk about what we call as the signed ranks. What we do in the signed ranks is, whatever is the rank of the whatever is the sign of the difference, you give the same thing to the ranks. So this is a positive 2.5. This is also a positive 2.5. Whereas because the sign here, the difference is minus 4, the rank also I make it as minus 7. The same thing I do here, minus 5.5, minus 2.5, minus 8, minus 9, minus 5.5, and minus 2.5. These are the ranks that I am giving. Now what we are saying is, the value of t which I have to find out is, for that you find out the sum of all the positive ranks. There are only 2 positive ranks. So the sum of all the positive ranks is 5. Whereas the sum of all the negative ranks, take them as absolute, 12.5, 15, 23, 32 and 840. So the sum of all the positive ranks is somewhere around 40. Now what I'll do is, I take the minimum of these 2 and I assign it to the value t. So the t is equal to 5. Now I'll come back to the formula. If the sample size n is less than 30, the test statistic is t itself. In this case, our sample size is only 9. I should not consider that value which is having a difference of 0. Only positive and negative differences need to be considered. So my sample size is 9, which is less than 30. So I'll say the test statistic is t, which is equal to 5 in this case. Otherwise, I'll go with this formula. If my sample size has been greater than 30, then what will I do? Let's say it is 30 or 30-40. I'll say 5 minus n becomes 40. 40 into 41 by 4 divided by square root of 40 into 41 into 81 by 24. So this comes out to be your Z value, and you will compare this Z value with your critical value and take your decision. But in case of the first, where the sample size is less than or equal to 30, you are comparing it with a separate table which is specific to Wilcoxon signed ranks test. The critical values again for Wilcoxon signed ranks test are based on the sample size, which is 9 in this case, and the level of significance which is 0.05 or 5%. Corresponding to that, a critical value will be there. If if the t statistic is above the critical value, then I'll reject the null hypothesis and say that the difference of the medians is not equal to 0. Otherwise, I'll go ahead with the null hypothesis. I'll fail to reject the null hypothesis, and I say that the difference of the medians is can be taken as 0. So this is one more test that would be helpful for us. Right, here also we did not do any kind of mean calculation, variance calculation, any of these things. It's just a simple ranking to the data values. So for this kind of a situation, we can take the help of Wilcoxon signed ranks test. So it can also be tested with respect to the median, because instead of subtracting two different data values, what I do is I subtract the median from all the values. So I take the same process. Every value is subtracted from the median, and after that the ranks are being assigned, and after that I can assign a signed rank, then add up all the positive ranks and separately, and add up all the negative ranks and take their modulus separately. The lower of those two, I'll take them as the t value and look at the sample size. If it is less than 30, I'll directly say that my test statistic is a t itself. If the sample size is greater than 30, then I'll use that formula to find out the test statistic. And again, z value comparison of the z statistic with the critical value corresponding to the z to take a decision. Then we are talking about a third test, which is the Wilcoxon rank sum test. Signed rank test is different from rank sum test. Here I am directly making a statement that the two populations have equal medians. What's the difference between this test and the earlier test which we have done? There we have come out with a statement that the differences between the two values, two sample pairs of data will have a differences whose median is equal to 0. That is more applicable to a paid sample kind of a data, whereas this is more applicable to two independent data sets. Two independent samples, what we are saying is they have equal medians. Two independent populations, we are making a statement that they have equal medians. The same thing if I apply it to 3 or more samples, I depend on Kruskal-Wallis test, which is like our ANOVA analysis. Alright, sometimes this becomes, people will directly use a word called Mann-Whitney-U test for this. Again, it's the same kind of a test. It looks identical in all the cases. In this also what we do is rank all of them high to low, but the only thing is combine all and then rank. Don't look at two data samples separately and don't do the ranking separately. Combine all and rank. I'll take an example and demonstrate it to you. But some things are, it does not require normally distributed population. And the good thing is it has an efficiency of 0.95, almost 95% compared to the parametric test. So there's no difference using a Mann-Whitney-U test or Wilcoxon rank sum test versus an equivalent parametric test. Equivalent parametric test is nothing but comparison of the sample means. This is the way the test goes. Now, if I say these are the two different samples I am looking at. The braking distance for 4-cylinder vehicles versus 6-cylinder vehicles. Let's say I have taken how many? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The sample size 13 here, a sample size 12 here. Now, if I want to say that these two samples have equal median, I want to say whether these two samples have equal median. What is that I am doing? You combine all these 25 first. Temporarily combine all the 25. And after you have combined them, start assigning the ranks. So out of this entire 25, because this is the least, this is getting a rank 1. Then this goes to be the least, second least, so it gets a rank 2 and so on. The entire 25 items will be given the ranks in this manner. This is given a rank of 23 and the one that gets 25 is the highest out of the two lots. So you give the ranks like this. And after you give the ranks individually like this, you simply add up all the ranks. 17 plus 11, 28 plus 6, 34, 54, 58.5, 78.5, 79, 88, 108, 122, 129.5, 130, 145, 145, 168, 180.5. Here I am getting 180.5 as the sum of all the ranks. Similarly here 28, 51, 54, 63.5, 81.5, 82.5, 107.5, 130.5, 132.5, 133, 137 and 144.5. Now let's say this is what I got as the ranks between these two sets of values. Now what we are saying is, if this is what is the sum of the ranks, I can very well try to find out this particular values and then finally arrive at my Z score for this. Okay, what is that I am doing in terms of arriving at my Z score? N1 13 into N1 plus N2 plus 1. 13 plus 12 plus 1, 26 divided by 2, which makes my mu equal to 169, which is the mean of the ranks will work out to 169. The standard deviation of the ranks is working out to square root of N1, N2, 13, 12, 156 into N1 plus N2 plus 1, 26 divided by 12. 13 into 12, so this becomes 13 directly. 13 into 13 into 2, so it becomes 13 into root 2. So root 2 is 1.4, so almost around 17. Let me round it off, right, or 18. 18.2 happens to be the standard deviation. Now what I can do, my Z value is R. R is, from the note here you are seeing that it is the sum of the ranks of the sample with size N1. With size 13, I want to find out the sum of the ranks of that, which is 180.5 minus mu. Mu is 169 divided by standard deviation 18.2. So all I am getting is around 11.5 divided by 18.2, which is somewhere around 0.6 or something. Now my Z value has come out to be 0.6, and all I am looking at is the critical value. And because this is the normal distribution, the critical values at 95% confidence level or 5% level of significance is minus 1.96 to plus 1.96. And because my test statistic Z value is 0.6 and it lies between minus 1.96 to plus 1.96, which means it does not lie within the critical region. So I need not reject the null hypothesis. I am failing to reject the null hypothesis, and I can very well make the statement that the medians of both these independent samples are more or less the same. There is no difference in the medians of these two sets of independent populations. So that is the kind of power that can be brought out using our Wilcoxon rank sum tests. Just like the way we have used a test for comparing the means, this test is helpful for me to compare the medians between two different independent samples. But these formulas have to be followed. These have been derived based on various assumptions, and we don't need to get into the derivation aspects of all these. If I am using a statistical tool like Excel or SPSS, all these calculations are directly taken care of by them. Otherwise, even if I am using any other manual based algorithm to to identify, or manual calculation in this case, I can do it in this way, and finally I can make my conclusion regarding whether the medians are more or less equal or not. The same thing if I am extending it to 3 or more independent populations. As long as it is 2 independent populations, I can talk about Mann-Whitney U test. But if I am going for 3 or more independent populations, I am talking about a Kruskal-Wallis test. Again, here also, but with more, just like an ANOVA analysis, in case of ANOVA also, in case of up to 2 samples mean, we were using either a t-test or a z-test. But the moment we have seen that the more independent populations have come up and we have to test the means, it was following an F statistic, which is actually a test for variances. The same logic I am extending it here. If I want to test for the equality of the medians between 3 or more data sets, I cannot use a Z statistic as I have used in the earlier case. It follows again a chi-square statistic, right? And the test statistic for me goes like this. R is the rank corresponding to each one of them, the sum of ranks, and N1 is the size of the sample. And this N becomes the total samples. So this equation will lead me to a H value, which is a chi-square test, and we know that in case of chi-square test, we find that the critical value is found based on level of significance as well as degrees of freedom. So degrees of freedom are number of independent samples we have minus 1. If I have 3 independent samples, the degree of freedom will work out to 2, and accordingly. Now let's see how do we work it out on our data. And the minimum requirement for executing this test is every sample should have a minimum of 5 values, because this boils down to a chi-square test. And in the chi-square test, if you remember, when we have used the concept of converting categorical value into a chi-square test, we talked about the minimum expected frequency to be 5 for each of the categories. The same logic here, there should be a minimum number of 5 data in each of these categories. Only then this is applicable. Now, what are we doing as a part of this entire test? Here we are talking about, if I want to find out whether the medians are uniform across small, medium and large whatever cars. Now these are my datas. These are the samples for small cars, these are the small samples for medium cars, and these are the samples for large cars. Now I want to see whether the medians across the three sets of categories of cars is more or less the uniform. So my first step is club all the data. Then give a combined rank, just like the way we have done in case of 2 different samples, 2 independent samples. Now I have clubbed all of them, and these are the ranks. Now what you do is add all the ranks for each of the samples independently. So you have 2 elements for each. You have N1, which is the sample size. So in this case probably 10. And you also have R1, which is the sum of the ranks of all the sample ones, of all the elements of sample 1. Similarly, you have N2 and R2. Similarly, you have N3 and R3. That's the next step. Once you have all this, you add up N1, N2, N3, which will make your total N. That would be your total sample size. And using that, what you can very well do is apply this formula. You try to calculate a value of H using this formula, 12 by 30 into 31, and you have to find out what is your R1 squared. probably R1 squared, whatever it is, by 10, which is the sum of all the squares of all the ranks. So you add up all the ranks and then square it. R2 squared divided by 10 plus R3 squared divided by 10, because the sample size is 10 in each of the samples. And this particular value you subtract 3 into n plus 1, which is 31. And whatever that comes out will be your H value, which is nothing but it's your chi-square statistic. And what you can do is find out the critical value from the chi-square test corresponding to 5% level of significance and k minus 1, which is 2 degrees of freedom. Try to find out the critical value, and based on that identify your critical region. And if you see that the calculated chi-square value is within the critical region, you reject the null hypothesis and say that the values are really the medians of each of the 3 data sets are completely different. Otherwise, you cannot reject the null hypothesis, and you have to go with the null hypothesis, which says the medians of these 3 data sets is more or less uniform or equal. So that is so the equivalent of an ANOVA test is what is being brought to you by the Kruskal-Wallis test. Right. So we have looked at this example. Then we also talk about just like the correlation, where we the parametric view of correlation, where we find out the means and variances and all. If I want to talk about the correlation on a non-parametric model, where probably if my data is not having a normal distribution, or the sample size is very, very less, in those kind of cases I can resort to a rank correlation mechanism, where the process is very simple. Let's take an example. Anything, first you rank both the data items separately. If you are given the raw data of 2 different samples, you find out their corresponding ranks without clubbing the data. Individually you find out their ranks. So for example, these are the ranks of the first one and the second one. Then you find out the difference in the ranks. 6 minus 4 minus 7 6 1 1 minus 4 and 1. These are the difference in the ranks. Then you square these ranks. 36 16 49 36 1 1 16 1. You square the ranks. Then you do the calculation, which is 1 minus 6 sigma d square by n into n squared minus 1. So these are the d squares. 36 plus 16, 52, 101, 137, 138, 139, 140, 156. This is my d square, sigma d square. 6 sigma d square by n, 8 items, into n minus 1, 7, and 1 minus. This is what is my test statistic. My test statistic in this case is 1 minus probably 6 into 8 into 7, 56, so almost 9, just rounding it out. N into n squared minus 1, sorry. So here it is not 7, 8 into 8 squared minus 1, 63. I'm sorry, 8 into 63. So 1 minus 6 into 156 divided by 8 into 63. So once I apply this particular calculation, I will get my test statistic R. Once I have got my test statistic, whatever is the RS, this is the test statistic that is being obtained. 1 minus 6 sigma d squared by n into n squared minus 1. What we can very well do is, whatever the R value that comes, if the n is less than 30, I am directly looking at what should be the range of R from the separate Spearman rank correlation table itself. If at all the sample size is less than 30, I can directly go with the Spearman's rank correlation table itself, which will give me the lower limit as well as upper limit, and I will see whether my value, whether my desired RS is lying within that limit or not. If it is lying within that limit, I will go with the null hypothesis. If it is outside the limit, I will reject the null hypothesis and go with the alternate hypothesis, which says these two are not correlated. But if my sample size is greater than 30, I can resort to this. Let's say I am going with 95% confidence level or 0.5%, 5% significance level. Then my Z is 1.96, and let's say if my data size is 37, root of 37 minus 1, root of 36. So it becomes 1.96 by 6. So my R value should lie between plus or minus 0.3. If my R lies between plus or minus 0.32 or something, then I say that then I will go with the null hypothesis and make a statement there is no difference in the correlation between the two data sets. Otherwise, I have to reject the null hypothesis and say that there is a definite correlation existing between the two data sets. So this is how I can use the rank correlation in a very effective manner. And sometimes people look at this is the greatest advantage which a rank correlation can derive. Even if the relationships are not linear, in some cases rank correlation has been very successful in identifying the relationships which are not linear. Whereas your typical Pearson's rank correlation coefficient, it was not at all effective in trying to find out the relationships which are not linear, because that formula of correlation will only talk about the linear relationship between two or more data sets, whereas your rank correlation in some cases is very effective in terms of identifying the relationships between the two sets of data which are not linear also. So if you are not bothered in any way with the underlying distribution, right, so that makes it a wide applicability for any kind of data sets. This Spearman's rank correlation can very well be applicable to any type of data sets very effectively, because all we need to do is convert the data into ranks and that's it. Or if your data is directly in the form of ranks, you can very well go further, right? The number of opportunities wise, rank correlation had quite a good number of applications compared to the typical linear correlation. But on the flop side, the efficiency rating is somewhere around 91%. So you definitely require a slightly higher sample size to typically bring in the same amount of efficiency which would be given by the equivalent parametric method. Only if I have a parametric data, quantitative data, it's if I am using a sample size of 100 to achieve a specific conclusion using a non-parametric method, I just need to use a sample size of 91 in the parametric method to bring out a similar kind of an effect. That's the kind of a difference we are talking of. Then one more test which we are interested in this context is the runs test, which is primarily used for checking the randomness in the data. I'm not so here we are trying to check whether there is a sequential run, basically like increasing every day, decreasing every day. So the pluses for some consecutive days, minuses for consecutive days. These are actually called as runs. Same characteristic going for some number of periods, and after that characteristic changing or no data at all. That is what we call as a run. So because these 3 days there is just a plus sign, we call this as one run. Then this is a second run. Only if it changes to plus and minus, then this alone is the third run, this alone will be the fourth run. That is what is the number of runs. And in a runs test, what we are doing is we are trying to find out whether the total number of runs, whether the data is random. If it is random, means my total number of runs will not be too low or too high. As long as my number of runs are lying within a particular interval, then I will take them to be more random. But if my number of runs are either too high or too low, I may say that there is no randomness, there is some kind of specific pattern in the data. And that is what is this z-test helping me in doing. So if I am considering N1 and N2 as number of positive runs and number of negative runs, right? Something is N1 where the number of positive runs are there and number of negative runs are there, and based on that I can very well find out what should be the mean number of runs and what should be the standard deviation of the number of runs, and based on that apply your z-test, where G is your actual number of runs and mu G you have found out and sigma G you have found out. Based on this you will arrive at the Z score. But of course this would be applicable when your sample size is greater than 30. When your sample size is less than or equal to 30, then the number of your test statistic is G itself. So this G you will compare against again a separate table which exists for runs test, a critical values table that would be existing exclusively for the runs test, and you would see if the number of the number of runs is lying between the limits which the runs test is specifying for your N1 and N2, and if it lies between that, then you will not reject your null hypothesis and you say that your data is random. Otherwise, if it is too high or too low compared to the limits which are given by your runs test table, then you will directly reject the null hypothesis and say that there is a definite difference in the randomness, which means the data is not random at all. But if my sample size is greater than 30, it will boil down to a Z distribution. So I can look at the critical values corresponding to my Z distribution, which are 1 minus 1.96 to plus 1.96 for a 95% confidence level or a 5% level of significance. And if that Z statistic, computed Z statistic, lies between minus 1.96 to plus 1.96, then I can very well say that it is not. Then I can very well say that this value does not lie in the critical region, which means I don't need to reject the null hypothesis. I can very well say that the data is random in nature. But if my G value lies outside the critical values minus 1.96 to plus 1.96, I have to reject the null hypothesis and I have to conclude that my data is not random in nature. Right, like this, if we see in this entire set of tests which we have looked at, we did not talk about the mean at all. We did not talk about the variance of the data. We did not talk about the proportions in the data. We only bothered about two things: the runs, the signs, the medians. And we did not even look at the distribution of the data. That is where we have the applications of non-parametric statistics. And of course, there are so many tools like Excel and SPSS which will help you in performing lot of non-parametric statistics on your data. And wherever it is not applicable, you have the formulas in front of you. Using these formulas, you can create your own models with respect to the non-parametric data, and based on that create your own conclusions regarding them. If you have any further queries on all these non-parametric tests, you can very well give me a call on the number which I am specifying below, 98480-12123. You can even email me on Vamsidhar@pacegurus.com, and I request you to visit my website www.pacegurus.com to get continuous updates on trainings and consulting activities, as well as the training videos in the areas of finance, investments, statistics and analytics using tools like Excel, VBA and SPSS. If you have any further queries, you can very well revert back to me. But of course, let me tell you one point here before I close this session. The non-parametric statistics is a big ocean wherein lots and lots of tests are available for various scenarios. But this is a decent introduction into 6 to 7 tests for different kinds of data comparisons, and we have tried comparing a parametric test with a non-parametric test by taking the equivalents in parametric tests. So at least this should help you in giving a very basic level introduction to the non-parametric statistics. Thanks a lot for listening to this session. Thank you very much.